Clustering was one big family of unsupervised learning. Here is the other, dimensionality reduction. Real datasets often have dozens or hundreds of features. That is both a problem and an opportunity. Let's see why. Picture a customer table with not 2 columns, but 20, age, income, visits, clicks, returns, and on and on. We simply cannot picture 20 dimensions, and many models slow down or get shaky when fed so many features at once. There's a deeper issue with a memorable name, the curse of dimensionality. Watch the same handful of points. On a line, they sit close together. Spread them into a square, and the gaps grow. Into a cube, and they are suddenly lost in a vast, mostly empty space. As dimensions climb, everything drifts far apart, and distance, which clustering leans on, starts to lose its meaning. Here's the opportunity. Many features secretly carry the same information. Height in centimeters and height in inches are, in truth, one fact wearing 2 hats. Plotted together they fall on a line, so 2 columns are really just one underlying direction. Most high-dimensional data is like this. The real structure lives in far fewer directions than there are columns. So here is the idea of dimensionality reduction. Take many features in, and produce just a few new ones out, while keeping as much of the real signal as possible. Not by throwing columns away at random, but by finding the few directions that capture what actually varies in the data. Why bother? 2 big payoffs. First, visualization. Squash the data down to 2 dimensions and we can finally see its structure on a plot, clusters and all. Second, speed and cleanliness. Fewer features mean faster models and less noise to trip over. There are 2 ways to get fewer features. Feature selection simply keeps a subset of the original columns and drops the rest. Projection, or extraction, is cleverer. It blends the originals into brand new combined features. The method we'll meet next, PCA, is a projection. Be honest about one thing. Reduction is lossy. Squeezing many features into a few must discard something. The whole art is to discard the least important part, keeping, say, 95% of the meaningful variation while shedding only a thin sliver of noise. In scikit-learn the pattern is familiar. We create a PCA asking for, say, 2 components, then call fit transform on X. Out comes a new array with the same rows but only 2 columns. The data, faithfully summarized, ready to plot or feed onward. To recap, too many features are hard to picture, and in high dimensions distance loses meaning, the curse of dimensionality. But features are often redundant, so we can reduce to a few new ones that keep most of the signal. It powers visualization and faster models, it is lossy by nature, and projection methods build new combined features. Next, we'll see the most famous projection of all, in pictures, PCA.